of the heavy star, which is the fate of the heavy star. And due to its heavy mass and large mass and the gravitational collapse and chemical composition, the density becomes increased inside the star and form a very compact degenerate core, and it leads to the burst of the neutrino flux to the outside, and the part of the neutrino energy is transferred to the matter around surrounding this core, and the visible explosion will follow the neutrino burst. So this so-called delayed explosion mechanism is very confirmed, the standard mechanism for supernova explosion for core collapse situation. So following this idea, so even if there is no any visible the signal, the neutrinos could be burst and arrive at the Earth from some explosion events, and then some visible explosion will happens and shows very bright signal, and it also contains very compact object with a certain key velocity from the explosion energy. And based on this delayed explosion mechanism, we can also predict the neutrino signal way before this visible spectrum. And this neutrino spectrum is also well confirmed by several observatories. And so this observation, this supernova observation observed in 1987, actually were confirmed this delayed explosion mechanism, and it predicts some formation of very hot neutron stars at the core, whose radius is around 10 kilometers. And the spectrum just of the neutrino after 1 second highly depends on this cooling process of this proto-neutron star, and at that very short time range, the most significant cooling source of this neutron star is a neutrino. So for given temperature of the supernova, about 30 to 50 MeV, the neutrino luminosity is given by this value for the environment of this compact neutron object at the supernova events, and this is very consistent with our observation. And after 30 years from the events, also we can confirm that the remnant of this supernova 1987 events is a neutron star from various different frequency range, some electromagnetic observations. So especially this radio wave frequency signal, we confirm that it is very consistent with the existence of a neutron star inside this dust by emitting very high energetic X-rays due to this high temperature compared to this dust temperature. And so this hotted region is denoted by this hot block. Therefore, this compact object lambda of the supernova events is naturally expected to be neutron star, because it is well consistent with the three-dimensional simulation for supernova explosion, and also well consistent with the theory of the neutron star around the age of this 34 years old. So our main laboratory, astrophysical laboratory, is proto-neutron star. So this is a relatively very hot neutron star, but how hot is it? So we can compare its thermal energy for given temperature and the Fermi energy given this energy density given by some Pauli exclusion principle. And it turns out that for this supernova period, the thermal energy is comparable with this Fermi energy, which means that this neutron star is a semi-degenerate situation. Therefore, because of such a very high density and high temperature, the neutrinos are generically trapped in the bulk, and the chemical equilibrium for the beta process is developed, especially for negatively charged pion and also muon, which leads to the tidal abundance inside the core. And you can, as you can see in this distribution function, as this negative contribution to the of the chemical potential. And for this given parameter, density and mass, we can easily calculate just a hand waving. We can provide just hand waving calculation for the abundance of the pion. And for this is the chemical potential of the neutron, and this is chemical potential of a proton, depending on its fraction inside neutron star. And it turns out that the pion distribution is around the 0.04 to 0.4 for the temperature around the 30 to 50 MeV, which is relatively hierarchically smaller than the pion mass. But of course, this is not the end of the story. In this paper, authors used some detailed nuclear physics technique and obtained that the pion abundance inside this neutron star is around 1% to the 5%. So although this abundance is relatively smaller than the abundance of the nucleon inside this proton neutron star, if we want to calculate the emission rate of some new particles from this neutron star, its contribution could be quite important. And usually, the channel to generate dark new particle is some dark Bremsstrahlung process, nucleon-nucleon interaction to generate nucleon-nucleon plus some dark new particle. So this is mostly elastic scattering plus some additional events. However, as you can see, these events, the final number of the particle is smaller than this nucleon Bremsstrahlung process. Therefore, this process is less suppressed by kinematic factor compared to this process. Therefore, even if the initial abundance of the pion is relatively smaller than that of the nucleon, this process could be quite important compared with this one. So that is one of the main some channel that I want to address in this talk. So then, what kind of new particle I will study? So I will focus on dark light boson scenario. So usually, of course, including fermion, in order to make some field very light, we usually require some symmetry. So let's consider spin zero particle. So most well-known some example which has some approximate symmetry is the axions. So axion is the standard of the singlet pseudo-scholastic freedom, which has so-called perturbative continuous shift symmetry, the U1p-Pechakin symmetry. And this shift symmetry is assumed to be only broken by some non-perturbative corrections. Therefore, the axion mass is relatively stable, and only some IR-dominated non-perturbative correction can provide effective potential to the axion. And the other interaction, namely axion and coupling to the quark or either photon and leptons, is all constrained from the symmetry argument. So if we just consider QCD actions, then axion mass is mostly given by this axion gluon coupling, digital coupling. And depending on axion model, we can also have some derivative coupling with axion to the U quark and D quark if we integrate all heavy quarks, which are not relevant for the some neutron star study. So here we have basically three main parameters: so FA, the decay constant of action, and coupling to the U quark and coupling to the D quark. And these coupling are mostly determined by so-called Pechakin charge of these quarks, so quantized with some small RG running effect. So we also take one more step to get the interaction between axion to the hadron. Then we also calculate the axion emission rate from the neutron star. So this is one example of the light particle for the scalar case. And the second example is the vector particles, whose the lightness is ensured by some gauge symmetry. So gauge boson has been one particle, And we can easily extend standard model gauge symmetry to the standard model gauge symmetry times some U1 new gauge symmetry. So although, of course, there are lots of possibility to introduce this U1 symmetry, which could break some flavor symmetry and so on. Here, I will just consider very minimal, the anomaly-free and flavor universal extension of the standard model, so-called dark photon scenario and P-L gauge symmetry. So then at low energy, the relevant interaction can be written like this one. So we have some photon kinetic term and dark gauge boson kinetic term and their possible kinetic mixing. And if the standard model particle has some non-trivial charge under this U1 symmetry, then it has also some direct coupling to the dark gauge boson. Standard model particle could be included this dark current. So when we consider such a dark photon scenario, it means that the all standard model particle is just neutral under this U1 symmetry. While if we consider V-L case, the baryon number and lepton number is directly becomes the charge of the charge under this U1 symmetry. So standard model particle, especially electron and proton neutrons, all have a direct coupling to this dark gauge boson. So including this kinetic mixing and dark gauge charge, we can have some non-trivial interaction. And also, the mass of this dark gauge boson is allowed if we consider some Stekelberger mechanism or dark Higgs mechanism. And the smallest of this dark gauge boson mass, in some sense, natural, because one reason is that if we take a vanishing mass, then it has some enhanced gauge symmetry. And secondly, because we consider relatively very small gauge coupling, therefore, even if the dark Higgs vacuum value is relatively large, dark gauge boson mass given by gauge coupling times Higgs boson vacuum value becomes quite small. So these two scenarios, axion scenario and dark gauge boson scenario, are main target to test from the supernova exclusion. So as I said, because of the symmetry, some interaction is quite restricted. So only a few pre-parameters for each case, some one coupling and its mass. So for twisted axion case, just a one coupling to the nucleon is just one of the important coupling. So then if their mass is small enough, then from the supernova events, those particles also could be produced and contribute to the cooling. And if its luminosity is greater than the standard model contribution, then of course it strongly changed the stellar evolution. So neutrino spectrum could be changed significantly. Therefore, we provide a very conservative point of view, so-called the Lafayette criteria. So the standard model luminosity should be smaller than so new particle contribution to the luminosity should be smaller than the standard model luminosity, mostly given by neutrino for such a young neutron star. In the final slides, so I will also provide another constraint, but this is generic constraint for the to provide general argument to provide constraint of the new particle from this stellar evolution. So typically, for neutron star case and supernova case, there are lots of neutron. So some nucleon Bremsstrahlung process is mostly discussed. But relatively recently, there are many different works, including the different process at the different stage of the neutron star evolution and different initial stage, and also different the Feynman diagram. So I also contribute in many work, in many cases, including many other interesting work. So in this talk, I just want to focus on two stories. One is that axion emission rate from the supernova, including, highlighting some contact interaction effect, which was ignored so far. And secondly, I will discuss some dark gauge boson emission, revisiting some dark Bremsstrahlung process, and also including some pion-induced process. All right. So I will first talk about the axion emission. So as I said before, because of the high temperature and high density, pion abundance is non-negligible, and it can contribute to the emission of the new particle, in this case, axion. So this is one of the traditional diagram, and this is a relatively new diagram. And in this work, authors calculated contribution of this diagram to the actual emission rate and compare this with this one. And they conclude that this contribution could be important, and in some sense more important than this actual Bremsstrahlung process. So this provides one of the important the motivation to study the implication of this prior initial study in more detail. And actually, this coupling, GAN and GAP, it could be derived from this quark level Lagrangian density. So at this just above the QCD confining scale, we have a light quark UD, and S is irrelevant here. So the action decay constant and CU0 and CD0 are both relevant coupling. And after confinement, we can obtain the coupling between axion and hadrons following the so-called chiral perturbation theory argument. So we can take some derivative expansion with some symmetry argument, and taking some very lightest nucleons and mesons. So this is some allowed Lagrangian density. So this action kinetic term and pion, proton and neutron kinetic term and mass term, which mostly respect isospin symmetry, and also it includes pion. And most relevant interaction is axion to proton coupling and axion to neutron coupling. And also there is the coupling among axion, pion, neutron, and proton, which is suppressed by 1/F5. And there are also other coupling. So this CAP, CAN, and CAPN are all calculated from the this UV some parameter, CU0 and CD0. And of course, it's, this FA just played over the overall scale, so it doesn't contribute to the CAP and CAN and also CAPN. Also, they are just calculated from the this C parameter is just calculated from the CAU and CU0 and CD0 parameter. Okay, and with some matrix element whose value could be calculated from lattice calculation. And please note that this CAPN coupling, coupling among axion, pion, and nucleons, that is proportional to the CAP minus CAN, so not the independent parameter. And actually, this value actually reflect how much this coupling and this action model violate some isospin symmetry between proton and neutron, or U-quark and D-quark. And for each term, they contribute to the diagram. So emission rate. So the first term contributes to the, this diagram is induced by this one. And the second diagram is induced by this one. And this third diagram provides this contact interaction. So and this is the reason I call this contact contribution. And in the previous work, only these two diagrams are considered, and this diagram is missing. So one of the just one simple motivation is include this new contribution and see how much this contribution is important. So actually, these contact interactions contribute not only this pi interaction, but also Bremsstrahlung process. We also have this kind of interaction with this vortex, right? So then, but still, this contribution was ignored in the previous calculation. So the question is why? Why this contribution usually ignored? So I will explain the reason from the for the Bremsstrahlung case first. So for this diagram, so I will just focus on this upper part, and this pion is an official pion whose role is momentum exchange among this initial nucleon. So this is official pion, and this is on-shell the proton, and this is on-shell nucleon, the neutron. And action's energy is typically given by the background temperature of the this neutron star. So this temperature is order of the action energy and also order of the action momentum, and that is much hierarchically smaller than neutron mass, nuclear mass, and also relatively hierarchically smaller than this momentum, typical momentum of this incoming nucleon. So this is naturally, this is naturally Bremsstrahlung, right? So Bremsstrahlung means that the energy of this radiation and momentum of the radiation is hierarchically smaller than the typical energy and typical momentum of this scattered particle. So we can calculate this diagram just using the ordinary Feynman rule. And then, as you can easily identify, and as we learned from the some quantum field theory course, when this action energy becomes small and small, there is some enhancement effect from this internal propagator. So in this internal propagator is is proportional to the 1 over omega a when the omega a is small enough. So this, with the help of this internal some enhanced propagator, this diagram could have additional enhancement factor compared to this just the contact interaction without any enhancement factor. So that enhancement factor for the matrix amplitude scale is given by k pi square over omega square. Here k pi is the this operational momentum, which is given by some typical momentum exchange of the this incoming particle, and that is mostly just given by the elastic scattering. So the typical momentum, thermal average typical momentum, so given by mn times temperature. And this omega A, the actual energy, is typically given by temperature of the neutron star. So this ratio, the enhancement factor, is given by neutron mass, nuclear mass over temperature. And even if the temperature inside neutron star is large enough, high enough, it is still hierarchically smaller than this nuclear mass. So it provides a relatively large enhancement factor. And this is the reason why this contact interaction for this Bremsstrahlung process is usually ignored. But this pion process is becomes important, and so we have to also check whether or not this contribution is important. But situation becomes quite different for this pion-induced process. There because of two reasons. One is that pions is no longer off-shell. This is on-shell, which means that pion's momentum, k pi, is smaller than, its value is typically smaller than the momentum of this off-shell pion. So this pion momentum is typically determined by this thermal average energy. So k pi is given by square root temperature times m pi. On the other hand, this k pi is typically given by square root mn times t. So there is an additional enhancement factor, right? Suppression factor for this one. And secondly, this becomes more important. So action energy is no longer very soft. So its energy should be greater than, usually should be greater than the mass of this pion. Because still this pion mass is hierarchically smaller than this nuclear energy. So this scattering is mostly the elastic scattering for the pion case, right? So action is mostly given by this pion energy. Therefore, pion energy, of course, should be greater than the pion's last energy, which means that when the pion mass is greater than temperature, then action energy should be greater than the temperature. So for this enhancement factor, this is no longer enhancement factor because k pi becomes smaller compared to smaller than the previous value, and omega a increases compared to the previous value. So if we enter some typical value in the thermal environment, k pi square over omega e square is given by the temperature over m pi. So actually, the contact interaction could be more important than this non-contact interaction if we consider this pion-induced scattering process, Thomson-like scattering process. So we performed more detailed calculation, including this some coupling model parameter. So this Ca pi minus, it can be expanded like this one. So this C plus and C minus is just given by these two ordinary diagram. And the previous work just take this one. If we include this the contact interaction, then contact interactions own the contributions, and also there are some mixing terms contribute to this matrix amplitude and its scale. And as you can see, this additional kinematic factor E pi, of course, is greater than P pi. So typically, this kinematic factor becomes greater than this one. The only remaining thing is this model parameter. So if the axion model is highly isospin symmetric model, then Ca pi n becomes 0. However, if axion model is highly axion model break isospin symmetry strongly, then this C pi n becomes sizable. So these contributions becomes quite important. So depending on some model, we performed the analysis depending on the nucleon neutron temperature, and it turns out that when the isospin symmetry is strongly violated, then this contact interaction contributions becomes nearly 4 times or 5 times greater than contribution without these contact interactions. So this actually is not the end of the analysis. Just this work just encourage the study on the axion emission for the spiral process in more detail, considering all the nucleon, the medium effect, and also all the possible diagram from the model construction. Okay, so this is just the part for axion. So I will discuss the gauge boson case. So yeah, this is a Lagrangian for the dark gauge boson. And as I said, I take two models, so U1 dark boson scenario and U1 B-L gauge boson scenario. And B- case, most of interaction is given by their charge. Neutron, proton, and electrons are most important particles, and they all have their own charge. So for B- case, we just neglect epsilon effect. On the other hand, for dark boson case, because the standard of particle is completely neutral, so kinetic mixing term is the most important parameter. So we keep this kinetic mixing for dark boson case. Then including this, just the direct coupling and this the mixing impact, we consider some effective coupling between this some electron, proton, and neutron, and this dark gauge boson for transverse mode and also longitudinal mode, including medium dependent effect. So compared to the axion case, most important thing for this dark gauge boson scenario is that because of a same spin nature, so this dark gauge boson can easily mix it with this ordinary photons. Therefore, the propagator of this photon becomes quite important, especially when you consider this very highly compressed neutron star environment. Electron thermal loop becomes very important. So it provides effective so-called plasma mass for the this propagator of the photon, whose value is proportional to this Fermi momentum of the electron. is typically given by 100 mega electron volt inside the neutron star. So we could calculate this self-energy of the photon following the various symmetry argument and the considering medium effect. But roughly speaking, we can argue that the gauge boson, which coupled to the electron, becomes very heavy, as you can see in this mass range. So it's very comparable with the temperature of the supernova. So let's consider some dark photon scenario and p-mass gauge boson scenario in the basis that the kinetic mixing term is rotated away. So then we have the the dark photon, the standard model photon kinetic term and the dark photon kinetic term, dark gauge boson kinetic term, and its mass term, and the coupling between dark gauge boson and standard model gauge boson to the some meta fields. So for dark photon case, so electron and proton has some same gauge boson combination, like as you can see here. And that is still true for p-mass case. So electron and proton also have the same gauge boson combination. So while the gauge boson coupling to the neutrons is quite different from electron and proton. And then what's the effect of this same combination? The effect is that because of the electron thermal effect, so the gauge boson, which coupled to the electrons, becomes very heavy compared to ordinary just ordinary photon or just the gauge dark gauge boson, whose mass is hierarchically smaller than 10 MeV. So this proton, which means that gauge so in the medium, this combination becomes heavy if we turn off this gauge boson mass term, and this combination become heavy, and proton coupled to the gauge boson, just exactly the same combination. So there is no direct production of the dark gauge boson from the proton, because gauge boson just coupled to the heavy degree of freedom. And this is also true for the p-mass case. But if we turn on this mass term, then this combination is not exactly massive degree of freedom because of this mass term. So this proton can couple to the not only this heavy degree of freedom, but light degree of freedom, whose coupling is proportional to this dark gauge boson mass over this plasma mass, when this dark gauge boson mass is small enough. Therefore, when we consider production of some dark gauge boson from this nucleon, especially proton, then the coupling highly depends on this dark gauge boson mass. And this is not true for the coupling to the neutron, because neutron coupling, especially when you consider p-mass gauge symmetry, is just a tree-level coupling, and this combination is not altered by some gauge boson coupling to the electrons. So for this, the Lagrangian density in the vacuum, so we could calculate the effective coupling between this dark gauge boson and the fermions, the electron, proton, and nucleon, including all these some environmental effects. And taking some the symmetry, the polarization tensor for transverse mode and longitudinal mode, we obtained the following general conclusion. The first is that the production rate of the dark photon and p-mass gauge bosons in both cases are different for different polarizations. So as you can see, so actually environment break the rotation symmetry significantly, right? So only some three-dimensional rotation symmetries remain. So the longitudinal mode and transverse mode is split, and that is reflected by the self-energy for the transverse mode and longitudinal mode. And also for B-mass cell gauge boson case, the effective coupling of the proton and that of the neutrons are quite different. So that is the most significant effect of the matter. So if we remove the just matter, then proton coupling and neutron coupling are exactly the same. They are all just the proportion to the baryon number, B equal 1. However, because of the matter effect, the combination that coupled to the proton is mostly become heavy. So neutron coupling, gauge boson coupling to neutron is significantly greater than gauge boson coupling to the proton. So that is the most significant effect of the matter for B-mass cell gauge boson scenario case. All right, so this is the end with some physics. So I will explain the result. We could calculate some nucleon Bremson process, which includes various different type of the vortex of the external dark gauge bosons, and that includes internal Bremson and also contact interaction. So because calculating all the diagram without approximation is a very, very tedious job, so we take this multiple expansion of this dark radiation emission. So in terms of the velocity of this incoming nucleons, which is typically given by square root T over M1, Mn, and over the 0.1. So it is still a good expansion parameter. Then I will briefly explain what kinds of new contribution is achieved from our work. First of all, so previous work, so usually use some software radiation approximation, in which this Bremson is nearly Bremson, so that we can separate some nuclear process and this Bremson vortex. But this actually captures only some classical limit of the Bremson, i.e. the independent of the spin of this dark charged particle or dark current. And in this work, we actually note that there are also non-negligible spin-dependent contribution, whose value is given by this additional factor. Okay, this is M is the matrix element. So if we take a relatively low temperature, then this low temperature could be smaller than this kinetic energy of the nucleon. Because if we consider neutron star, then this nucleon kinetic energy could be dominated by thermal energy and also some Fermi energy. If we consider very low temperature, then Fermi energy could be much greater than the thermal energy. So this contribution is suppressed. So spin-dependent contribution is safely ignored. However, if we consider some supernova environment, then temperature is high enough so that this becomes order 1. So spin-dependent contributions becomes quite important. So the physical implication, physical meaning of this spin-dependent contribution could be obtained from this Pauli Hamiltonian. And we know that so usually this particle has its kinetic terms, and also the coupling to the some gauge fields whose value is proportional to this velocity. This is classical current contribution, and also it has some coupling to the magnetic fields whose coupling is proportional to the spin. So we usually interpret this as a magnetic moment, right? And this magnetic moment, so oscillation of the magnetic moment also leads to the generation of the radiation, not only just the dipole radiation. So this magnetic moment contribution could be calculated, order of this magnetic moment contribution could be calculated by some order of estimation, and it turns out that this magnetic moment contribution for dipole order is given by this some usual classical contribution times energy of this dark gauge boson over its some internal energy. So yeah, this becomes some correct interpretation. And secondly, we also note that if we consider B minus L gauge symmetry case, so the coupling between neutron and effective coupling of the proton is quite different. So why this is important? If the proton and neutron coupling is very similar, then the dipole order, when you consider some multiple expansion, some dipole order contribution is cancelled with each other. This is a reason. I mean, this is caused by the some same mass, similar mass between the neutron and proton. So generically, if the center of charge for this collision process is nearly the same as the center of mass, then dipole contribution is vanishing, and whose matrix element is proportional to the coupling, the charge of the some incoming nucleon 1 and charge of the incoming nucleon 2. So if they are same, that means the center of charge is the same as the center of mass, then this dipole contribution would be vanishing. And this is exactly the same argument that gravitational wave is not produced at the dipole order, because the center of charge is just the same as the center of mass. Therefore, if we just assume the effective charge of the neutron and effective charge of the proton are the same, then dipole contribution is vanishing. But in actual situation, for B minus L gauge symmetry case, they are different. So dipole order is non-negligible. And if they are same, then we have to consider some quadratic order. So for this model, we can compare. So we can compare the incoming some nucleon effective charge. And as you can easily identify that, if the incoming nucleon are the same species, if we consider neutron and neutron, then of course, effective charge of the neutron and effective charge of the neutron and effective charge of the proton and proton are the same. So they are all vanishing. So we have to compare effective charge of the neutron and proton. So for dark proton scenario, we easily identify that the effective coupling of a neutron is just 0 because it's chargeless. And then, so dipole contribution becomes important to give a constraint on the gauge boson emission from the supernova. On the other hand, if we just consider U1B symmetry, U1B symmetry case, electron does not couple to the any gauge symmetry, any these dark gauge bosons. Therefore, the neutron coupling, this effective coupling is just the same as the proton coupling. So dipole order is cancelled. So quadrupole order is important to generate these dark gauge bosons from the supernova. Then what about U1 B minus L case? So U1 B minus case, because this U1 B minus L gauge boson also coupled to the electron, so it leads to the significant difference between the coupling of the neutron and coupling of the proton. So dipole contribution is not here like that. So dipole contribution is non-negligible. So compared to the previous estimation, we obtain a relatively stronger constraint for this some more smaller range, the region of the coupling. So the previous work about the U1 B minus scenario didn't consider this immediate effect carefully. So which leads to some wrong conclusion. So we pointed out some immediate effect could be quite important to update this constraint. And also, yeah, we identified that the constraints are different for transverse mode and also longitudinal. And We also actually studied some constraint from the neutron star, which is a remnant of the supernova 1987A. But in this talk, I will skip this part and just uh, I will talk about the pion-induced emission process for this dark gauge boson. So as you can see on this diagram, so because we have the nucleon and dark gauge interaction, and also we have the pion nucleon dark gauge interaction. But from this kind of diagram, we could calculate the emission rate of dark gauge boson from the this pion nucleon scattering. So pi minus and p plus scattering. And the corresponding the luminosity, the emission rate, as the function of the emitted dark gauge energy given by these blue colors. If we include additional some meta effects for the pion energy, not only just the free particle energy. And as you can easily identify that this figure, the energy of this dark gauge boson should be greater than this pion mass, and mostly its average value is around the 200 MeV, so which is much greater than the ordinary temperature of this neutron star. So this means that this could provide more stronger constraint on the higher mass range of the dark gauge boson compared to the case without considering this pion-induced process, right? So we considered all these kinds of constraints to provide this some money plot for in the x-axis given by dark gauge boson mass, and y-axis is given by some coupling or kinetic mix parameter. So here, let me consider some Yuan mass cell case first. Here, so I just mentioned some cooling argument before. So if this dark gauge boson take care of the energy, part of the energy of the core, and leave this core, then temperature of the core decreases very fastly compared to the standard prediction. So it is constrained from the observation of the neutrino spectrum. And that gives a constraint on this kind of red color from the pion in this process and nucleon ordinary Bremsstrahlung process, including all the dipole and medium effect for transverse mode and longitudinal mode. On the other hand, if we consider pion this dark gauge mass larger and larger, then this dark gauge boson is no longer stable. So even if they are produced from the core, it can just decay outside this some core collapsing some largely reduced star, or inside this the star environment. This also can provide interesting constraint. First of all, this star, this dark gauge boson X can decay to charged leptons, especially the electron and positron. And if its mass is large enough, then maybe it can decay to muon and antimuon. But because of usual energy of this dark gauge boson production from the pion production, it would not decay to muon plus antimuon. And also it can decay to neutrino and antineutrino when you consider B1, B1 cell scenario. But for the this charged particle, mostly this positron will lose its energy by scattering with a background some plasma, and also will eventually annihilate to the radiation. So because its energy is quite large, so around the 200 MeV. So before it lose most of its energy, it will radiate a very hard X-ray, hard gamma ray spectrum. And we can compare our observed gamma ray spectrum with the prediction of this gamma ray spectrum from the supernova event with this dark particle. We can provide some interesting constraint on the coupling of this dark gauge boson for given mass. And this blue range is the constraint from that kind of argument. On the other hand, if this dark gauge boson leave this core but decays inside this core-collapsing stars, then it provides some sizable energy to the surrounding material, which means that it triggered the explosion of this supernova, not given by the energy of the neutrino. So as I said before, usual the delayed explosion mechanism. So part of the neutrino energy is transferred to the surrounding material and it leads to the explosion. But in this case, so this X gauge boson, B-mass gauge boson decays, and so most of the energy of this B-mass gauge boson is transferred to the surrounding material, so trigger the additional some anomalously very strong supernova explosion. So by comparing with this kind of some explosion energy with the simulation and also some supernova remnants and there's some the remnants velocity, we provide some relatively interesting constraint like this green range. So and also there are another constraint. So I just focus on larger mass range. So usual in the usual delayed the explosion mechanism, neutrino would be produced first, and we get the neutrino signal well before the photon signal. However, if the this X emitted, generate is leave this core by taking some energy and decay, then this X can decay not only to the E plus E minus, but E plus E minus plus some gamma ray. Therefore, the main reason that the usual gamma ray signal is well so-called delayed compared to neutrino signal is that there is a very strong interaction inside this material. So photon some is actually trapped in this core, so it will leave later. However, so most of our energy is given by this X particle, and just it decay outside this some surrounding material, then it does not need any time dilation. So if we just see supernova 1987A, we identify that there is a time delay between neutrino spectrum and photon spectrum. But if there is this kind of a new particle with this coupling and this mass, then we expect that this photon signal is just around the neutrino signal. So that is inconsistent with the observation. So from that kind of a supernova 1987A, the photon spectrum and neutrino spectrum, we could provide very interesting constraint in this large mass range and very smaller coupling. So we can also provide the same constraint for the dark photon case, but this general behavior is given by the fact that neutron is completely decoupled from this the dark photon production. So only proton coupling is important to provide this constraint. So as the dark gauge boson mass becomes more and small, its effective coupling to the dark gauge boson becomes weaker and weaker. So that has this kind of it has this kind of some generic behavior. But the situation is also the same. So we can give a constraint from the high energetic gamma ray and also some anomalous large supernova explosion energy, and also some prompt gamma ray signal just after neutrino spectrum, like that. And also we provide some additional constraint from the pion-induced the production process. So okay, so this is so my last slide. So we discussed the implication of the supernova explosion for the new physics scenario in the standard model, especially very light, relatively light dark gauge boson scenario, actions, and also dark gauge boson. So we found that some kind of contact interaction, spin-dependent multiple radiations, and also correct treatment of the effective charge of the standard model particle in the medium, and also the energy spectrum of the emitted particle in each lifetime could provide very important and interesting observational consequences. So we can prove that the kind of parameter range from the supernova events. So of course, stellar object is quite complicated. So our approach is, in some sense, very hand-waving. But we hope that this kind of argument will encourage some more detailed study of the production and interaction of this some particle beyond the standard model with some this compact star in more detail and obtain some more concrete result. Right. So this is it. Yeah, end of my talk. So thank you for listening.
Okay, thank you for your very nice and comprehensive talk. Okay, let's. It's time for discussion and some questions. If you have any, I think that today is because of I think the main organizer, the computer was not working. So because of that, Kimiko.
Hi, can I see the
Hey.
page 50?
Could you say again?
Can I see the page 50?
50.
50? Yeah.
Yeah, this one.
Yeah. Could you please tell me the reason that the constraint is just the range, not the lower limit of the coupling? I saw that the higher coupling is suppressed, should be constrained more, but this is just a range, not the lower limit on the constraint on the coupling.
You mean why this constraint on the coupling is just seems to be shifted, right?
No. Why the higher? Why the large coupling value is not constrained?
You mean this range? What
because,
is why? Yeah, why not constraint?
Yeah. Why only this thing?
So here the main reason, I mean main argument is that so compared to the previous work, we identified that effective I mean the luminosity okay, so production rate of dark gauge boson is enhanced compared to previous discussion, and so that is the reason why it has more stronger constraint on the smaller coupling. But so as you can see in this some dashed line, so above this coupling, there is no strong constraint. The main reason is that so produced this dark gauge boson particle is the can just trap it inside this core. Because large coupling actually means that production is very active, but absorption or losing the energy process by the scattering with some surrounding material is also very effective. Therefore, we have to, we want to know that some situation that some new particles, so as you can see here, new particle is produced in the core and take the energy and leave the core. then it contributes to the cooling of the core. But if this X cannot leave the core and just trapped inside the core, then it does not contribute to the cooling. So that range is the coupling is not constrained in general. So that is the reason why there is some upper bound, there is some low bound and also upper bound. But the situation is the same also. So in this case, for given coupling, our estimation says that its effect is more also significant for the absorption process or some scattering process to lose their energy. So if the coupling become here in correct treatment, it can more easily trap it inside the core. So does not contribute to cooling, so there is no constraint. So that is the reason why we don't have any constraint above this range, differently from the previous calculation.
Thank you very much for clear explanation. It is nice to know that the smaller coupling is, constrained. Thank you very much.
Yeah. Thank you.
Thank you.
Okay, thank you for your discussion. There are more questions. Okay, I think it's interesting to point out this pion-induced emission, in particular for heavy dark gauge boson and axion. And so the signal depends on the decay length of this heavy particle. So if have you also considered the case when the dark gauge boson does not decay into electron and positron pair? I mean, this even if we decay below
you mean
below electron threshold, you don't have a constraint?
Yeah, we actually do not provide any constraint here. Of course, in general, there could be, I mean, so there are two possibilities. One is that this gauge boson usually, of course, can decay to neutrino when we consider B- cell gauge boson case. If we consider dark boron case, then at least it does not have any the coupling to the neutrino, so its lifetime could be much longer than the usual U1 B- cell case. Anyway, lifetime of the U1 B- cell case is just determined by mostly determined by its decay to neutrino, because that is usually always allowed in our parameter range. So in that case, maybe we can actually also study the neutrino spectrum, right? But in that case, I'm not quite sure how much we could distinguish this neutrino spectrum and also ordinary neutrino spectrum from the supernova explosion. So in the at least supernova 1987A events, it would be quite difficult to see the spectrum itself. Of course, there are a few data. Yeah, but if we have some more some large number of data, maybe we can also obtain some spectrum of the neutrino from the supernova. Then maybe we can study some new physics signature in the neutrino spectrum. And and maybe other possibilities that I'm not quite sure. Maybe this type of gauge would also maybe can oscillate to the photon. And I don't know how much that effect could be significant. I mean, for case if this gauge boson lifetime is very long, then through the electron, I'm not quite sure. So how much some real oscillation effect to the dark gauge boson to photon could be could provide some meaningful constraint. Yeah, I didn't think about that.
Okay, so there might be similar oscillation for this axion, right? So
axion case, with the help of the magnetic fields, because of the spin is the difference of the spin. So with the magnetic fields, it can easily convert to each other. But it has some same spin, so I think it can easily convert.
Okay, so I think that there's a question from the main organizer.
Hi, thank you for your comprehensive talk. I wanted to ask, have you thought about putting together all these astrophysical constraints with some precision electroweak constraints on pion physics or U1, because your U1 is mixing with hypercharge, you have an epsilon coefficient, and you put together both constraints, so you get something
right. So
restrict parameter space.
Sure. In general, that is completely true. So actually in this plot, I didn't show any such some terrestrial experimental constraint. That actually would be quite important. But as far as I know, maybe Sokun knows more about that and more about better than me. But as far as I know, that this value, this range of the dark gauge boson coupling, and also this mixing parameter, the terrestrial experiments constraint would be not so significant. Therefore, I think that those constraints would be here, or some line here like that. So, I should find it, but as far as I know, there is no some meaningful constraint, at least in this range. Maybe that is the reason why. Maybe another reason why we just cut here. So just to separate the constraint on the coupling from the terrestrial experiments and the astrophysical some observation. And maybe this is another reason. This is another reason why astrophysical so-called laboratory can play the important role, because this parameter range cannot never studied in the terrestrial experiments. Yeah, but I'm not quite sure what value is.
It depends on the value of epsilon, I suppose.
Right.
Or of the mixing with the.
So at least in our case, we don't introduce any, for instance, Higgs and any some flavor violating charge. So very minimal. So maybe flavor constraint or some electric constraint would be very, very weak for these scenarios, at least.
Maybe the beam dump experiments gives some significant constraints on the B- cell, but still it is significant when the mass is above the 100 MeV. And it's
100
not
MeV,
so,
I see.
above the 100 MeV, because we need the decay rate as short as this detector size. So beam dump size. So above the 100 MeV, it would be significant, but not as much as this 10 to the 5 or 10 to the -6 decoupling strength. But I'm not sure. Well, yes, maybe beam dump for such a terrestrial experiments gives us some bound, but here we only concentrated on the astrophysical bound and comparison just between them. So yes, in the future we should add the result in our plot, but just our main purpose is to compare the astrophysical bound. Is it your answer for you? Your question?
Yeah, great. So I think the chemical, you still have hands. You have
yes.
a question? Okay.
Yeah, you consider the spin 0 and spin 1 case. So for spin 2 massive graviton case, is it possible to give the strong constraints to their couplings? Especially
So
spin 2 is very different.
so I think so at least so so actually the astrophysical constraint on the new particle basically depends on model. But just as you saw in my presentation, I just want to highlight the symmetry argument to restrict coupling and just to see what's the effect of this symmetry. So when you introduce some spin 2 particle, and then of course there should be just some corresponding symmetry. I mean, some maybe extra dimensional, some maybe KK graviton, I don't know. Anyway, that kind of symmetry usually restricts the coupling. So in general, we can apply the same argument. One big difference is that I don't know, maybe Hyun knows much better than me, but I don't know some good example that some spin 2 heavy particle has some selected coupling. I mean, this U1 B-minus gauge symmetry or U1 dark boron scenario case, the coupling to the matter is very selective. So gauge chart is just quantized. We can take 0, 1, or 1, 1 like that. But if we consider spin 2 case, maybe like a graviton, its coupling could be quite universal, I think. So proton, neutron, and electrons are all coupled to this spin 2 particle whose coupling is proportional to this energy or whatever. I don't know. I don't know the good example.
Yeah, maybe it.
Maybe it may be closer to this B minus L case because this G prime couples to baryon and lepton together. So, but I think there is maybe in terms of interactions, maybe it's closer to axion-like particle because it's the derivative interaction. Yeah, but I don't know. Maybe yeah. But
the
there
coupling
are some issues for light massive particle, massive spin 2 particle. There might be some issue, some unitarity issue. So.
For non-universal.
Also,
right.
Yeah. Also here, I think the G prime, light G prime case, you consider kind of Stickelberg mechanism to give mass to this particle. Maybe if it is normalizable, maybe you can introduce some dark Higgs mechanism and then dark gauge boson, dark Higgs emission might be also relevant, probably, right?
Right. So actually, yeah. So at least maybe if I just consider small gauge coupling and small Higgs vacuum value, then also some darker Higgs also could be produced from the star. Of course, at least if we just this U1, then Stekelberg mechanism itself is okay, right? But if we consider, this Proca if we consider dark Higgs mechanism, at least in our work, we usually just assume that gauge coupling is small enough, so that even if dark Higgs sector is heavy, so gauge boson could be light enough because of smallness of gauge coupling. So dark Higgs or some coupled dark matter, whatever, could be heavy enough, which are not produced from the star. But if we just allow the other parameter, so that Higgs could be also light, or Higgs could couple to the dark gauge boson, not only dark gauge boson, but dark matter, then yeah, maybe it could be more, maybe in some sense rich or complicated, and maybe you can connect it to the dark matter scenario. And also this Higgs can have a direct coupling to the standard model Higgs. maybe h scale, yeah, phi scale like that. So maybe that kind of interaction could be related with some maybe collider searches. I don't know. Yeah.
Okay. Okay. Are there more questions? So if there's no more question, I think I understand better your nice project. I think that you are continuing on this project, right? I think that I see some work in progress. So
Yeah,
I will see more paper in the future, right?
I hope so.
Okay. Yeah. Okay. Thanks for your participation and so giving a nice talk. And Sokun, also nice to see you even online. Hopefully we want to
Yes,
see
nice to see you.
Again in Korea. And I think it's Proca, so-called Proca seminars. It's a good, the right topic that you choose today, right? So Proca seminar, Proca gauge field. And
I respect program.
it's supposed to be a joint seminar between our colleague Dumitru Ghilencea in Romania, and also I just joined recently. So thank you for your hosting this nice seminar in this Proca series. Okay, so in 2 weeks we'll have another seminar from Korean. So I think I will announce it to all of you. So you are all welcome to join. You're welcome back to join this seminar series in the future. Okay, so Dumitru.
My apologies again. My apologies again for the crash laptop, which delays the seminar. So sorry for that again. Now I have to go to the new laptop. I have to move all my stuff to the new laptop.
Okay.
It was very unfortunate. Thanks a lot. Thank you.
Yeah, thank you
very much.
No problem. Thank you. Yeah, bye.
So,
And yeah,
the recording now.
okay.
Okay.
You record.
Thank you
Okay,
very
you
much.
can start.
So
Okay, thank you.
Thank you.
Keep going. Which would also be on axion, right?
Yeah,
Axion physics. Yeah.
Hyun,
Okay.
right?
Thank you very much. It was very nice talk. Thank you.
Yeah. I think that we need to invite Dumitru to some seminar. I mean, it's not Proca, but another seminar.
Well, we can keep inviting other people as well to join us. Maybe at some point we can end up with some collaboration on mutual themes of interest. I was did some work on dark gauge bosons. The constraints from both dark matter and electroweak constraints. So in that case, I could see that they were strong enough, and you could get the constraints on the parameter space from both directions. And okay, that is quite some time ago. It was slightly different from the scenarios that you do, but yeah. So your talk is interesting, and it also suits the title of the seminar actually. Proca gauge bosons. Okay,
I think
so
we need to
very much.
bring Proca in any topics of this series. Proca.
It's not difficult because
In
it's
it.
pretty much. Yeah. You mentioned some points, the Stuckenberg mechanism here. And that reminds me that there are this kind of dark gauge boson can be part of in Kerr space-time. You can have such gauge boson very naturally, but it's not as slight as here. Like a gauge boson which mediates gravity in addition to the graviton itself. but it doesn't work here because it's supposed to be heavy, but it could contribute to dark matter. So anyway, as someone said, also you can have a dark Higgs, and that complicates matters even more for the constraints. But again, if you put together astrophysics and electroweak precision data, I think you definitely can constrain the model much more. Well, it depends, as you said, if they overlap or not. That's the question. If there is an overlapping region or not, depends on the mass and the couplings. Anyway, thank you very much again. So we look forward to the next seminar. And again, my apologies for the delay for the crash laptop. Thank you very much.
Yeah, thank you. Thank you. Okay.
Thank you for invitation. Yeah, I also enjoyed many questions and environment.
Okay.
Okay, thank you. Bye.
Bye.